Abelian processes are a relentless geological force where the wind acts as a primary agent of planetary erosion, capable of swallowing entire landscapes. Migrating sand dunes have constantly threatened critical human infrastructure, requiring manual intervention just to keep roads and railways from being buried. The mechanism behind this threat relies on deflation and saltation. Wind entrains loose sand, causing it to bounce across the surface. This chart shows saltation dominates, accounting for 50 to 70% of wind-driven movement versus creep and suspension. Because saltation is dictated by fundamental physical laws, the desert operates as an unstoppable, mathematically complex moving force. To defeat it, we first have to figure out how to track it. Today, to understand this massive threat, scientists map the desert using high-tech UAVs equipped with multi-temporal LiDAR systems. These laser pulses easily penetrate sparse vegetation to map the exact topography of the sand underneath, generating highly accurate, bare earth 3D digital elevation models. This visual shows a two-panel digital elevation model comparison of a massive dune field between 2009 and 2010. You can clearly see how the entire landscape physically shifts over a single year. This diagram shows the PSTP algorithmic method, using a mathematical search radius to match points from the original dune to new locations. Looking at this hillshade comparison, target arrows calculate the precise speed and direction of the dune's slip-face centerlines down to the centimeter. Humanity successfully mapped the desert's migration, diagnosing the massive threat. But simply measuring the movement of millions of tons of sand doesn't neutralize it. The actual solution deployed on the ground to stop these dunes skips million-dollar spatial algorithms entirely. Invented in the 1950s, the straw checkerboard relies on nothing but dead wheat and rice stalks. Workers manually shove the dry straw halfway into the sand, forming a continuous grid of 1 meter by 1 meter squares across the vast dunes. This layout functions as an aerodynamic trap. Wind hitting the straw barrier is forced sharply upward, leaving a calm, low-pressure zone inside. The barrier strips the wind of 90% of its kinetic energy, causing entrained sand to drop heavily into the grid. The 1 meter dimension perfectly balances physics with engineering economics. If the square is larger, the wind sinks back in and lifts the sand. If it is smaller, labor and material costs surge without adding any protective benefit. This elegant aerodynamic hack neutralizes the exact physics of saltation, using geometry to achieve what a brute force physical wall cannot. Stopping the kinetic movement of the sand is only phase one. The dead grids actually trigger a biological chain reaction. Those windbreaks inherently trap wild grass and vegetation seeds blowing through the desert, holding them securely in the low-pressure zones. Over 3 years, the dead straw rots. It breaks down into a natural, moisture-retaining fertilizer that feeds those trapped seeds. The decomposing straw is eventually completely replaced by living grass checkerboards, turning barren dunes green and permanently anchoring the earth. Our greatest defense against the shifting earth pairs macro-scale, high-tech digital observation with micro-scale, low-tech engineering that turns dead straw into a living ecosystem.